Good morning. Um, Hideo, talked about this very interesting combination of microwave, which I've been following, but very kind of superficially. And I wish I had a deeper understanding of the microwave because, kind of one of the dreams for us in photonics has always been doing nonlinearities at the single photon level. And as we saw, it seems kind of almost trivial for them and something that's much harder for us. What I'm going to tell you about a little bit is a combination of kind of, I'd say, thinking about the crowd, it's somewhat tutorial, somewhat kind of maybe something I think is pretty interesting in the latest work, and then something that I would say has kind of bothered me for almost 40 years that I've worked out. And it's a very simple calculation, but it's something that I think is intriguing. I think I've spoken with Steve Harris about this a number of times, and perhaps maybe the microwave single photonics community can provide insight and maybe explain to me where my confusion is. So our resonators in photonics aren't in some sense are very different from those in the microwave domain. And here I just show kind of a very generic one. I sometimes actually call this the nonlinear photonic atom, only because it has resonances. You tune close to one of the resonances, you can excite nonlinearities very much like you can in atomic systems. And the one I'm talking about, and you saw, well, I didn't, unfortunately I wasn't here, but probably some of you saw Amir's work, which talked a lot about Chi2 type interactions in these. Ali Reza may be talking about this as well. But really all these systems, there's really been a kind of a revolution in the last, I would say, 10, 15 years. And you saw from Kerry Vahala's group yesterday from his talk that we can now get Qs that are really remarkably high. And so there's two ways we're getting confinement here. We're getting confinement is that we've actually captured the light, it's circulating around this cavity, but we've also captured it in the sense of these microresonators, because if you can look at the cross section, it's of the order of a micron squared. And so you can excite light here at kind of relatively modest powers. It can be maybe even a few hundred milliwatts, and it's possible to have 100 watts circulating around the cavity, which is pretty astonishing, actually. And the materials are such high quality that they can actually support 100 watts circulating around in a micron squared. And so, of course, that allows you to do certain kinds of nonlinear optics, but you can also go to the extreme limit is now, when I was in Bob Boyd's group, he always said nonlinear optics is only going to become important and massively used. It's still not massively used, but hopefully it's getting there. If you can do it nonlinear optics at the laser pointer level. And back then, the way we did it was always with fluorescein doped boric acid glass. Probably none of you have heard about it, but you just take this low temperature glass, you dope fluorescein into it, and it has this about a 1 or 2 second lifetime. It looks like a glow in the dark thing in terms of the green, but you could actually do nonlinear optics at the milliwatt level, which was great. Problem is it had about a 1 hertz response time. Everything we're talking about here, these are effectively materials that have instantaneous response. And so it's kind of astonishing now that we can go at like way below a milliwatt and actually see very strong optical nonlinearities in a material in which the nonlinearity is purely electronic. So as I said, I think maybe I'm only focusing on Chi3 materials. And so you can reduce any process to four-wave mixing in a Chi3 material. And there's a lot of different processes. Here, I'm just keeping it as generic as possible. So four-wave mixing, where does it come from? Well, you have a third-order nonlinearity. 3 waves mixed together to create your fourth. And that's where the term four-wave mixing comes from. And so as I draw on the picture here, let's say this is one particular process. Of course, there could be others, but this is one particular one. And the way you draw is you have energy conservation, which in this case, this picture, which we all use in the community, is that we annihilate this red photon, a blue photon, we create a yellow photon and a green photon. And so that means we have energy conservation. It's actually kind of interesting because we always talk about it in terms of photons. And this is one of these things that, again, I've known for a very long time. I still don't know how to answer this correctly. Maybe Steve can answer it, or Marty. But the fact is this relationship in terms of energy conservation actually comes out of the Manley-Rowe relations. And you only get the photon picture when you just divide by h bar. And then you say, well, number of photons, it works out. But actually, it's coming from the classical Maxwell's equations. And still to this day, I don't completely see how this photon picture, which actually tells you about how these photons are correlated, actually drops out of the Manley-Rowe relations, which is a completely classical result. But that's, again, another thing that maybe someone can explain. What? Sure. Right, but what's surprising is that when so we write that picture down, and I understand, from the Manley-Rowe relations that you could interpret it that way, but we then extract that, and it works at the single photon level too. Okay, we'll talk about that more. I mean, at least it's an interesting idea. But certainly when you're talking about superconductor resonators, you don't worry so much about the momentum matching in the same way that you have to in optics. And that's because, when you look at that picture here, this is still many wavelengths going around here. And so for us, actually, momentum conservation is critical. And when you're thinking Chi-2 processes, it's a pretty straightforward process, because really you just have to, if the propagation constants have to add up, and all you worry about are the linear optical properties. But in four-wave mixing, there's additional properties, cross and self-phase modulation, that actually make this delta K non-trivial to satisfy. And so this part may be fairly easy. This part typically is not. So, but fortunately, we have something that can help us do that. And you saw from Ryan's talk yesterday, he introduced this concept of dispersion engineering, which actually, we talked about a number of years ago. And it actually was first, has been discussed with optical fibers and so on. But it was really in the chip-based systems where you could really engineer this dispersion, which could allow you to do this momentum conservation, which turns out to be really critical. And the difference between kind of optical fibers and these chips, these nano waveguides, is that typically the index difference between the cladding, which more often than not is an oxide, and the core, which could be, let's say, silicon or lithium niobate, is very large. And because of that very large difference, you get very tight confinement. And actually, when everyone was doing chip-based nonlinear optics, they said, this is great, you can do very high nonlinearities, but the dispersion was not quite right. But it turns out that roughly in the same ballpark, you might have to change your waveguide size a little bit. You can just use the waveguide dispersion, and it can be very severe to actually engineer dispersion and achieve the phase matching. And I think that's really what opened up, kind of four-wave mixing and why it's so effective in these waveguides. So here I just show an example. This is silicon, a little bit of an extreme example, but it just shows you different sizes of waveguides here, 350 by 1200, 400 by 1500. So the black is the bulk silicon. And it actually is completely normal. It actually doesn't become anomalous till out, I think, around 6.5 microns or something like that. But what we can see is you can get broad regimes of anomalous group velocity dispersion. And in fact, the dispersion, for example, of this red seems to have very little to do with the black. And that's, again, the key aspect. So two things. One is it can produce anomalous group velocity dispersion, which turns out to be very important for phase matching in four-wave mixing processes. But it also allows to produce, let's say, regions where you have very large normal dispersion, where maybe it was anomalous. And so by tuning that size of the waveguide, and you're not tuning very much, you can basically design the dispersion to be whatever you want. And so now this is implemented in all platforms. It's universal. It's not unique to a particular material. Early on, these microresonators were done in whispering gallery modes, where actually the light wasn't as tightly confined. And this is work that was kind of pioneered by Kerry Bahala's group. And then, we started doing forward mixing in silicon nitride and silicon. And these materials here, you could really just engineer dispersion. So silicon, again, which highly normal, was actually the first kind of chip-based device where you could do parametric forward mixing. In silicon, which was always thought to be a bad optical material, you could actually produce parametric gain. So all of a sudden, material which kind of thought of as you can't build a laser out of it or anything, now you can. And since then, and then, we hit silicon nitride, and that's the one that we've primarily worked in our group. But certainly all these different platforms have been studied. They all have certain advantages, disadvantages. Some have Chi2, some don't. But in all cases, they all have kind of their own characteristics. And, if you write them all down on paper, some of them appear to be better than others. I'm still, even though I've looked at a lot of them, silicon nitride still continues to be probably the best performing. And it's primarily for two reasons. One is that the loss can be really reduced to, I think, the lowest levels currently on chip, neglecting silica, which is a little bit complicated. But silicon nitride of all the platforms still has the lowest losses. Lithium niobate getting very close to that in terms of similar performance. The second part, which is a little more subtle, is that there actually is no appreciable Raman scattering. And so it's really a pure Chi3 nonlinearity, instantaneous nonlinearity, and that turns out to be pretty important. So here I've just identified four-wave mixing processes that you could imagine. So I'm going to actually cover three of them. So the first one is, where you annihilate, let's say you're pumping this microresonator with green photons here, and you can actually produce parametric gain for a signal and Idler photon. And these are crucial for building optical parametric oscillators, but also the curved frequency combs that you saw from Kerry, and I'm going to touch on both of those. The second one is just the reverse process. So it's now, I'm pumping with a red and a blue photon to create a degenerate photon. And if you look at that, you'd say, that's just this photon. And so the phase matching conditions are the same, but they're not. And that is because there's actually other processes going on, like self and cross phase modulation, which change that phase matching condition. So in fact, this process occurs in the anomalous group velocity dispersion regime. This process, you get the peak when you're in the normal group velocity dispersion regime. So again, this is very different from kind of Chi2 and other processes here, and it's really unique to the forward mixing. And so I'll talk a little bit at the end about self and cross phase modulation, and then there's also kind of the unitary, where you pump with two strong waves here, and you can actually do quantum frequency conversion between a signal and Idler at this point. It's something we do a lot of work, and we've been working in microresonators, but I'm not going to talk about that today. So let's just focus on the first one. So this is what the picture looks like. And again, I'm leaving out all the math, but this is what the gain profile looks like if I bring in a single frequency pump and I'm looking for the gain for a signal and Idler at this location here. And it has this very kind of odd looking plot where the gain kind of increases, it peaks, and then drops and vanishes. And where it peaks is precisely where the self and cross phase modulation of all the waves cancel out precisely the anomalous group velocity dispersion that you need for this process to occur. And it's right at that point where you get the peak gain. And again, as you increase density of the pump, this actually keeps moving out. So again, it's very different from Chi2 processes, where it certainly typically doesn't depend on intensity. So now I have this microresonator. I have an intensity dependent refractive index. So if I tune my pump to one of the resonances here, this is what the transmission, or you can think of the intercavity power, actually looks like. Okay, so now I start increasing the pump power. And what happens is, because you're changing the refractive index ever so slightly inside the cavity, and this is actually very much analogous to the cross phase modulation that you see in the superconducting microwaves, is you tune that resonance, the peak resonance there. And of course, that's what's done in microwaves. You can detect that and detect single photons. This is what we would love to do in photonics. And then if you keep increasing the power, what happens is the curve starts showing this kind of S-type shape. And this actually is a signature of bistability. And actually, when I was a graduate student, this was the first problem I worked on. And I was fascinated by this, but we didn't have any good system. We would do it, we'd take atomic systems and put them inside a cavity. Here you can do this in a truly microresonator system, and you can actually see this kind of behavior. Now I'm leaving out the thermal effects, which turn out to be kind of make this even more extreme, but this just gives you a rough idea of what goes on. And this branch right here is unstable, and so typically you have, you think this is a stable branch here and then a stable branch down here. And it turns out that if you look at this branch, it's actually, even that branch doesn't become stable. And that is because if you parametric gain, so this is modulational instability. If the signal and idler grow, exceed the losses inside the microresonator, they grow until they actually form an oscillator. But what's interesting is on the lower branch, it's also unstable. But it turns out under suitable conditions, you can actually excite an optical frequency comb. And if you saw Kerry's talk yesterday, he went in a nice description of how this happens. So again, I could spend the entire talk talking about these combs. This has been kind of one of the hottest areas in nonlinear photonics for the last 10, 15 years. And it's a lot of beautiful physics, a lot of complex dynamics, chaotic dynamics, and so on. But the key takeaway here is, using these microresonators, we can generate these very high quality optical frequency combs. So here I just show just two examples is all I'm going to show in terms of this data here. But it shows for the case of a silicon microresonator that has a Q of 32 million. So this is about as high as you can get, at least in a tightly confining waveguide. And what you see here is you turn up the pump power, and at 73 microwatts, you see the threshold turning on. This is an optical parametric oscillator. Again, this is a purely electronic nonlinearity, and we can actually, build an oscillator there, which is 73 microwatts of power. If you keep turning up the power, it becomes chaotic. You have to do this little ballet with the tuning, but you can get onto this lower branch here, and under suitable conditions, you generate this mode lock soliton frequency comb. So this is actually a pulse that's circulating around the cavity. It has a hyperbolic secant squared. Fourier transform of hyperbolic secant is a hyperbolic secant. So the spectrum is also a hyperbolic secant here. So you can see that single line here that's pumping the system. And I've generated a comb, which is now spanning close to an octave in this particular case. And the total pump power here is 2 milliwatts. I used to, and not so much anymore, but I used to work in ultra-fast physics. We have a 0.5 terawatt laser system in my lab, and that was always called extreme nonlinear optics, because you can do high harmonic generation. Well, to me, this is extreme nonlinear optics. I'm starting off with a single, pump at just, a few milliwatts, and I can generate roughly 1,000 new frequencies, and it can span an octave. So the ultra-fast community doesn't believe that's extreme nonlinear optics, but anyway. So one of the key parts is that really the way I think I would say almost everyone else in the world other than us, the way you would do all the tuning here is you start off with your single frequency laser and you tune into your resonance at this point here. And it turns out because of thermal effects, you sometimes have to tune pretty far. And there's things that people have done is to say, okay, I don't want to tune my laser that far because sometimes you have to tune at 50 gigahertz. It's not easy to keep it single frequency and tune in and do the little ballet that's required to generate the comb. But nevertheless, so people do other techniques where they have an external modulator that allows them to tune it, an AO modulator or so on, and allows them to actively and fast tune it. But there's a simple way, which is to use microresonators where they have, they're already very small, and you can deposit a platinum heater on there. And it turns out because this is so small, you can actually tune the cavity at about 1 megahertz. So you can tune it extremely fast. And so you can just keep your single frequency laser, if it's a very high quality laser, a 1 hertz line width, let's say you're trying to do frequency metrology applications, then it's very easy to tune into resonance by just tuning the resonator to your laser there. And so that's everything we've done. And then all you need is just a waveform generator on electronics that's tuning the current, and the currents required is of the order of tens of milliwatts of electrical current. So it's very easy to do. And here I just show an example of what this looks like. So we have our pump laser, it's fixed, but now we're tuning the microresonator. We tune into resonance, and what you see here is a lot of fluctuations. This is actually chaotic regime, but then all of a sudden it hops, and this is when it hops to that lower branch. Note that the intensity is pretty high. So here we're on the upper branch where it's getting, it's chaotic. And then it jumps down to the lower branch. And again, this is all transient. So you have to do some tuning to get back. So you tune in the forward direction, then backwards. Then you can sit on what are called these soliton steps. And these soliton steps, if you were to actually look at the spectrum, so for the case where you're on the one where, the one which we call the single soliton step, you can see the spacing here is roughly the microresonator spacing. If you settled on the other soliton step, you see every other line disappears. And this means that there's actually two pulses circulating around the cavity, exactly opposite one another. And you have a case where 3 out of every 4 lines disappears. And that corresponds to 4 soliton pulses. And we can easily just tune to one or the other and control this electrically. So you can really control the dynamics of the system in a very easy way. So now I'll get on to the part which I said at the title of the talk, which is coupled nonlinear devices. And this is something that we've been working on for the last few years, which is you take 2 of these systems that are generating combs, 2 microresonators, they produce these combs here. And you think with nanofabrication techniques that, you could make these identical, but it turns out, they can't. These aren't quantum objects. They're still kind of classical objects. And so just the fabrication uncertainty, and it turns out, as I always, like to say, that there's a lot of nano in photonics, is that a 1 nanometer change in the height of the waveguide leads to roughly a 1 nanometer shift in the 0 group velocity dispersion point. And so that shift is changing the dispersion, and that will change the conditions for forward mixing and phase matching. And so even when you make a wave for silicon nitride, the deviations across the waver will be tens of nanometers. It won't be flat. So you can never make a microresonator exactly the same. Not only that, if they're at slightly different temperatures, silicon nitride, for example, has a thermal refractive effect. Refractive index will change slightly, and so they'll never be exactly the same. But there is one very simple way of making them identical, or at least making the combs that are generated here identical. And that's just to take a small amount, couple some of the light from one to the other, and by small amount, a fraction of a percent. And it turns out that just coupling that little bit will actually synchronize these two. And you can then get combs that actually are perfectly spaced. And this is like a phase transition. So that's why I like to call it synchronization, which is really a phase transition. At least this configuration, it just looks like injection locking, but injection locking is just a form of synchronization. It's one special case. And the beauty of it is actually, if you looked at these very complicated coupled combs, it's these coupled Lujado-Lefebvre equations, really, you can numerically integrate them, but actually what you can do is actually, assuming you have solitons in both of them, you can reduce it to a very simple coupled nonlinear equation, which looks just like the Kuromoto model. It's quite beautiful because the Kuromoto model is the one that is kind of the standard model for modeling synchronization. And so what it says is our very nice system here, this complicated combs, these core frequency combs, obey exactly the same type of Kuromoto model. So all the synchronization effects that you see in this model here should also happen in our system. And so for the first experiments we did, we had 2 microresonator combs. And actually, they weren't even on the same chip. They were 2 completely different chips. And we actually connected them with a 20-meter long fiber. So these are 2 tiny little 100-micron devices separated by 20 meters, or at least optically by 20 meters. And we can control how much light we couple one to the other. And again, it's a very tiny amount. It's a fraction of a percent. But here's kind of the behavior, what you'll see. So if they're not coupled at all, and you tune thermally one of them with respect to the other, this is the relative frequency difference, let's say, of the two nearest comb components as a function as you tune the heater. So the red you can see just keeps tuning through. There's some point where it goes through 0 where it's close, but then it keeps going down. Plus and negative here come out the same. So it keeps going up. That's why it goes back up this way. But when you then couple, again, a small tiny fraction, you see that there's a phase transition that occurs right at this point here, and then they get locked or synchronized. And then, of course, if the difference is too large, just like the Kuromoto model, then they begin to deviate again, as if they were uncoupled. And so you can actually plot how much frequency tolerance is allowed as a function of how much transmission you put through the system. And so, not surprisingly, if you maybe put more light through, it tolerates a larger frequency difference. And this synchronization region is actually called, again, if you've studied synchronization, it's called an Arnold's tongue. So it's very common in mathematics to describe it this way, and I guess because it looks like a tongue. And so what you can see too is that, and this is a beauty of these systems, is we can model them incredibly well, is the blue line here is the experiment, and the solid line here is the theory. And so you can see this is a system, despite its complications, we're pumping these, we can model it really exquisitely well. So then you can do even more extreme, like subharmonic synchronization, where you take a comb here, which has, let's say, a harmonic spacing of a second comb here. Again, you leak a little bit of light through. And not surprising, of course, every other pulse will be leaking in, rather than every pulse leaking in before. But again, you can expect that perhaps there's synchronization that can occur here. And then there's the other version where now, pulses are coming in, and now, these pulses are going by very quickly because it's a much higher separation. But once in a while, you get some leakage here. And I wanted to connect actually with something that Ryan talked about yesterday here, which, Carrie talked about as well, is one way of interpreting the synchronization. So, right now it seems like black magic, but you can really think about it in terms of, let me hop to this point, is that I have a pulse that comes in here. And of course, it's very weak, but it actually, when it leaks in here, this pulse changes the refractive index ever so slightly. And again, it may be a very small amount. It might be 10 to the minus 6, maybe 10 to the minus 8. I think Amir was estimating yesterday for some of the systems that Ryan was talking about for trapping photons and so on. But it's the same behavior you can think of in the temporal domain, is that the pulse over here sees this index change, and that actually causes it to kind of get trapped into that region. And so if you think it, you could think in the frequency domain that I'm really lining up all the frequencies, and if they're close enough, they line up. But actually, in the time domain, you can think of it also, that it leads to synchronization. And these are all the Arnold tongues for all the different configurations. You could have 3 to 1, 2 to 1, 1 to 2, 1 to 3. But then, of course, you can also have harmonic ratios that also work. And again, you can have these different combinations here. And again, the beauty of it is that we can model these systems really well. So the blue dots here represent the experiments, and the red is the theory. So then I want to now go to like an extreme case of synchronization. And this was, again, Carrie talked about this yesterday, which is generating ultra low noise microwaves, and again, using optical frequency combs. So, the simplest way to generate microwaves, and this was done early on, is to just take 2 lasers and you separate them by your microwave frequency, and you just put them on a photodetector. Very easy to do. The problem is if you look at lasers, they actually have a shallow Towns line width, and that shallow Towns line width decays very slowly. It's a Lorentzian function. And so if you think about the noise that's created by interfering these two to create your microwave, it's actually pretty noisy. And so if you want even a reasonably good low noise microwave source by doing this, you need lasers that are sub-hertz, which, there's maybe a few places in the world that have these type of sub-hertz lasers. So this is not practical, that's for sure. And what was developed about 10 years ago is a really beautiful effect called optical frequency division. This was done mostly by the NIST group, is to have your 2 optical references, but make it much bigger, terahertz, 10 terahertz. And now what you do is you take an optical frequency cone that you've generated, and you lock, for example, this laser to the line of this frequency cone, likely here. And that locking actually fixes then all these frequency components. And so now this RF frequency is just given by this large terahertz frequency divided by M, where M is the number of modes underneath this. So this is called, not surprising, optical frequency division. It's very powerful, and you'd say, okay, so you've generated, microwave this way. What does that buy you? Well, when you look at the noise, not only is the frequency divided, but also the noise is divided. And so ultimately, if you actually look at the noise spectrum, it's divided by M squared, where M is the number of modes. And so you can get a huge enhancement that can be up to 10 to the 8th or 10 to the 9th reduction. Yep. So that's a good point. So up to, that's perfect because you're leading right up to my thing. So it's a good question, but still, when people do this optical frequency division, they still need very high quality laser sources. Because, what I showed you before, that's 1 hertz, and that doesn't get you anywhere close to kind of what a state-of-the-art sapphire or quartz oscillator can do. But this technique can. And so you still need very high quality lasers of the order of hertz. But now you can now produce a microwave signal that can now approach the best microwave sources today. And actually now I think they're beating all of them. And now this technique is now producing the best state. And again, Carrie talked about this, and they've done some beautiful work in this area. And actually this year, I think it was the April issue of Nature, there were 3 of these. And not surprising, this was driven by DARPA program, which my group was a part of. But also Carrie's group and Dan Blumenthal's group. But they in those cases, they were using actually lasers. So they were able to produce these very high quality hertz line with lasers to do this. So I'm proposing, and what we demonstrated here is a very different approach. So if you think about those other systems, it actually requires 3 lasers. You need 2 reference lasers plus the laser that's driving the comb. So it turns out to be 3. So here what I'll propose is a system where you can start from just a single laser and do the optical frequency division automatically. And the beauty of it is the laser doesn't even have to be that amazing. Certainly doesn't have to be 1 hertz to achieve very good performance. And it uses really the quantum correlations that exist with optical parametric oscillators, which is going all the way back to the beginning when you're thinking about the 4-wave mixing process. So what we do is we split off the laser. We're driving 2 microresonators. They could be the same, but they could be very different. And what we do is one of them is kind of on the upper branch, and it's producing an optical parametric oscillator, signal and idler. The other one, we adjust it so it actually produces a soliton comb. And now you can see that our 2-point reference is a signal and idler here. And again, we adjust the dispersion so that this signal and idler grow at this point of 10 terahertz apart or whatever. And then the microresonator comb can be in the microwave regime. And then we take it 1 step further, because what you see here is rather than doing all the electronics, which can be non-trivial to design, we just take a little bit of the OPO light and leak it into the soliton comb. In this case, you get synchronization here. Now, of course, the difference in frequency, this is like subharmonic synchronization by the factor of 500 or so. But it can be very easily done and straightforward. And this whole chip here is 1 millimeter squared. So you can automatically do the optical frequency division in this very simple circuit, so to speak, photonic circuit. And one last part, which I haven't talked about too much, is typically the electronic locking that is done is typically, let's say 100 kilohertz. Here, the locking bandwidth for synchronization is of the order of 10 megahertz. So you have a much higher locking bandwidth. So it's a much tighter lock than you get in these systems. So here's kind of just very quick indication of how this works. We have one of them tuned to the OPO, the other the soliton comb. So the 2 OPO, if you look at what is the signal that's leaking into the soliton comb, it looks like this. It's just a periodic source. But of course, now here you can see that if there's a small intensity-dependent refractive index change, where when it's high, the refractive index will be a little bit higher, and then when it's down low, it'll be a little lower, and that traps the soliton. This is very much like, or analogous to the trapping that Amir and Ryan talked about yesterday. So you can just trap it, you can couple it, and again, the beauty here, the subharmonic ratio is about a factor of 500, but it really can work. And so here's the key points. So I think a lot, certainly the referees that reviewed it did not pick up immediately on this part, which is they said, oh, you're just generating a 2-point reference. But this is a very special 2-point reference coming from the OPO, because the 2 of these, the frequencies are correlated. Not only that, they share exactly the same cavity. So the pump if it moves, signal and idler move along with it. So any phase noise that the pump does gets imparted on both the signal and idler, and we're looking at the frequency difference. So it gets subtracted out or divided out, however you want to put it. And so mostly the pump phase noise gets subtracted out. And not only that, they share the same thermorefractive noise that you have inside the cavity. So both of those are tremendously reduced. And so that's why you really don't need an amazing pump to really get very good performance from the system. And so that turned out to be a key part. So here's kind of what the actual chip looks like. This is, Michal's group, which, we work with them in designing it and everything else. And you can see here that we have this OPO, Soliton. And again, we have this coupling waveguide, which takes a little bit of the OPO light, puts it up here. And so in this particular case, the Soliton was a 227 gigahertz, so it's pretty high frequency. But nevertheless, you can see the division factor that we get when you take the ratio of these two frequencies. The OPO is 7.7 terahertz, 227. It's supposed to give 32 dB. We see 31. And then you can take even to get a larger division factor, you go down to 16 gigahertz, which again, I could spend half a talk talking about how one gets a Soliton cone from the system, but you get a 54 dB reduction here. So I think I'm running out of a little time, so I think I'm going to skip, well, maybe quickly through here. So that represents kind of the first case here, but now we'll talk about kind of the reverse. And again, this is a system which really, a lot of this grew out of precisely work that was done here at Stanford with Ali Reza, Yoshi, Bob Beyer, which is these degenerate parametric amplifiers. And of course, in the Chi-2 case, you just have a single pump coming up and you produce a degenerate signal coming down. Here, we need two pumps to do this. So now you pump at two different modes, and then you have a degenerate signal that's right in the middle. And sure enough, if you look at where does the peak gain occur for the degenerate signal, the green lines here represent where the pumps are located. In all cases, actually, the gain peaks at other locations in the degenerate. But when you're in the normal GVD regime, it actually peaks there. So that's what you design your system to actually operate. So what you do is you have your two pumps operating in the normal GVD regime, and then you should expect to get a degenerate signal. So this is a phase-sensitive amplifier, so you should also, at least below threshold, be able to produce squeezing. So this is just kind of what the expected squeezing looks like. And then when you go right above threshold, you can see that this is sort of like a cat state where you have a signal up here, a signal down here. They're separated by pi, so it's a little bit like a cat state. And it's an open question whether these OPOs can actually generate these cat states. But certainly below threshold, you just get ordinary squeezing. And so we did these experiments where we actually had two of these, a squeezer and an oscillator, and they were identical microresonators, but we operated one, we detuned it, so one it went above threshold. And so that forms our local oscillator to the squeezer here. So it turns out to be very nice. So this is what the one ring looks like above threshold. There you see the degenerate signal. And then the other one, that's the squeezer. There's obviously no signal there. But then you can measure the squeezing. It wasn't huge, 3.1 dB, but it just shows here that this is non-classical properties below threshold. Now, above threshold, there's also quantum properties. And again, group here at Stanford has done a lot of pioneering, much of almost all the pioneering work in this area, showing this for Chi-2, that when you go above threshold and you look, you actually find that there's kind of two possible states that the system can display. One in which, if you look at the phase condition for peak amplification of the signal, it's the phase of this pump, phase of this pump, minus twice the phase of the signal here, because I have two photons here. So you can see, and this has to be equal, it turns out for this case, minus pi over 4. That's where you get the peak gain. So when you go above threshold, there should be this phase relationship where the phase between them differs by minus pi over 4. However, there's a factor of 2 here, which suggests that you can switch the phi of 3 by pi, and it won't change this phase condition. So that means every time you stop and start this, you put your hand in front of the pump and start it up again, the signal will randomly switch between these two possible phase conditions because this is initiated from quantum noise. And so here we just do the experiment where what we do is we alternate, we turn on the pump and then we consecutive generations of the signal, we interfere on a unbalanced interferometer. And you can see here, we're always generating the OPO, but the interference between them is randomly changing. And you can show that it really behaves in all respects like a quantum random number generator. And what you could do is you begin coupling them. And of course, this is what was motivation for Yoshi's work, and the work done here at Stanford was to build an Ising model where you have a spin. We have a spin here where the system, depending on the signal, can be 0 or pi, so it behaves much like a spin. So it's a relatively simple system. They've demonstrated 100,000 spins. We're nowhere near that. But at least this is all optical. There's no, and it's on a chip. So now we have two of these, and we can actually couple these together. And then we can adjust the phase between these. So we have a coupling waveguide, we have a little heater there, and so we can change that phase coupling. And what's interesting about it is if they're in phase, then both the oscillators will actually always turn on. If they are 180 degrees out of phase, and it's hard to tell here, but when you look at the interference between them, oh, I'm sorry, these are each oscillator, and this is the interference pattern. So that they're always kind of adding together. When they're 180 degrees out of phase, the coupling, then they're destructively interfering here. And so you see, not surprising. And then you can actually line it up to close to 90 degrees, and then it gets kind of random again, which is, again, kind of interesting as well. So now I'm just going to finish up and talk a little bit. And these are more, nothing's published. These are own personal thoughts over the last few decades on self and cross phase modulation with single photons. So the system, typically if you want to see cross phase modulation, and again, I'm assuming the meter beam is classical here, unlike the superconducting case, but we have a meter beam and we bring in a quantum field here, and we want to see if we can measure the phase of this meter beam and see, if it's significant. And so the output field, if you go through all the math, will look like the following. So you have the input amplitude, and then you have this nonlinear phase shift that occurs. And then there's this nonlinear part here. And now you could put it in the following form, where the gamma here is actually the phase shift per photon. So clearly, if I have one photon here, the argument is I'd produce roughly 1 radian of phase shift. So that's pretty significant. So, well, maybe Misha and Vlad and Vulicic's group have gotten close to this, but in photonics, we're very far. So this gamma here, it turns out to be an important quantity, and you'd think, oh, it's just a constant. It's not important. If you do kind of very simple calculations, you can show that when this phase shift becomes of the order of 1, this actually changes a lot of the dynamics of this very simple system. So if I take the expectation value of this meter output here, I have an expectation value of this exponential e to the I gamma photon. So again, doesn't seem too surprising. So if I look here, though, at the cross phase modulation for a number state, so let's say that that weak field here is a number state. Well, e to the in, that's just an eigenfunction of the number operator, and so it's very easy. You can see this is what you get from the classical result that we're really familiar with. It just says output will experience a phase shift, which goes like to this e to the I gamma times the photon number, which is exactly what we get from classical. Now, what's interesting is when you go to the coherent state and you evaluate that operator here, and for those, maybe most of you have done this, but you apply the Baker-Hausdorff theorem here, which is a little bit of mathematics with dealing the matrix of these. And it turns out you get a very interesting result, which is this. Now, this result, and I'm going to hop to this, if I assume the phase shift per photon is small, this becomes 1 plus I gamma, and I recover kind of the classical result. So that's good. But what's interesting is when it's not small, you get a very different result with a coherent state than you might expect for the number state. It's actually completely the opposite of when we do, at least when I, done quantum optics. I did quantum optics. Len Mandel was my professor, and he was always telling us all the time about, distinguishing between classical and quantum regimes. And it's funny is that when you put in the number state, you get actually the classical result. But when you put in the kind of classical field, the coherent state, you actually get very different from the classical result. And I should say that this calculation was repeated. It's slightly different, I mean, parameters, but this was repeated by Jeff Shapiro. So this is kind of a somewhat famous paper, controversial paper, we'll say, and I'm sure Hideo has lots of thoughts on this as well, and maybe Steve, who we've talked to, but it's very provocative title. Single photon Kerr nonlinearities do not help quantum computation. So I don't know how this lines up with all the work that's been done in microwave signals, because they're already in this regime and it's working pretty well, right? But anyway, he does this calculation, and partly he assumes that the gamma here is actually, I'm sorry, I can't see it, but he assumes it's like of the order of pi. And so you can see he gets a result that's inconsistent with classical results. And then he does some other calculations, but I want to focus on that because I think this is the consistency that he sees in his system. And I think it's just a result of this. But, you know, I've talked to Jeff about it, but I don't know, there's an impedance mismatch. And so he sees it very differently. But anyway, so I think it resolves it. But what's interesting about this is there's something very different when you get into this regime, at least in the photonic regime, how I've done it here, between when gamma is of the order of 1, when you have the phase shift is of the order of 1. And I don't know if there's something that can be seen or observed in the superconducting circuits. It'd be very interesting. So this is my last slide, but this is something that I remember thinking about a lot when I was a graduate student, having a lot of discussions with Bob Boyd about this, which is if you take almost all transparent materials, chi3 is positive, or if you want to think of the nonlinear fractive index as positive. It's, you know, highly non-resonant. Every material you can think of, you know, you can even work with the noble gases, and the N2 or chi3 is always positive. So why is that? What's the intuition? Well, it turns out if you just do a full Schrodinger calculation and derive chi3 nonlinearity for a generic atom, okay, and what you'll find is that you'll end up with, at the end of your calculation, going through all the math, which is a lot of math, but you go through it all and you have these two terms. And you can show actually that these two terms have kind of, from this photon picture or Manley-Rogue picture, however you want to do it, talk about it, it can be classified in two ways. That this one here is up, up, down, down. So that's one four-wave mixing process that produces self, in this case, self-phase modulation. And then you have an up, down, up, down. So it turns out that if you look at the sign of these, again, for a generic atom, you can show that this one in the highly non-resonant limit is always positive, and this one is always negative. But this one, because it's two photon, is a little bit more resonant. So if you look at the resonance terms, it's quite a bit larger, much larger than this one. And so this is really the reason why almost all highly non-transparent materials have a positive chi3. So very generic, and you can show that. So that's nothing. But what's interesting about that is it suggests, because these processes, that in order to get the up, up, down, down, you need two photons. So if you have a single photon state and you're trying to see if you have self-phase modulation, you'll never get the up, down, down process. You can only get this one. And so what it suggests is that if you have two photon state and you measure chi3 or some nonlinearity, and then all of a sudden you reduce it down to one photon, not only does the nonlinearity change dramatically, it will actually change sign. And so the two photon versus one photon is very different. So again, this is just calculations I've looked at for a long time, but you know, I'm happy to entertain any thoughts if anyone has on these things, or if they can be observed in. But again, you know, this is Schrodinger system, so it's very different from the, you know, a quantum circuit that's being done for superconducting qubits, but I think that could be interesting. So I'll just finish up and acknowledge a lot of the experimental work that we saw here is, oh, and the latter part, my grad, that's just me, my grad students, I don't know if they might disavow it. But these are students that have worked on, and again, all the experimental work is done in close collaboration with Carl Lipson's group. Thanks.
We've got time for a couple of questions before we head to the break.
Yes, I have one comment and one question. So you're right, actually, in superconducting circuits, this what you call a cross-phase modulation is actually observed all the time in the quantum regime. And in fact, it's all the operation, most of the operations on the so-called bosonic qubits, cat states, and the like use actually all this difference that you pointed out between the coherent states and the single photon state. So this is put to use. But my question was rather concerning the frequency comb. So you were presenting the very nice experiments you did in actually synchronizing combs as this, if I have understood correctly, this is a pathway to, you presented this as creating microwaves that would be very coherent, but isn't the use, the application in reverse? Because we have very, very good microwave generators. Don't we want to, in fact, do the opposite, use the great phase coherence of these microwave generators and transpose them into the laser, make the laser stability much cheaper in some sense, isn't?
So you could, I mean, using electro-optic combs, that happens all the time. But what I'll say is they can get probably to noise levels, and you'll see in the near future, to noise levels using these type of techniques, which are 100 times higher quality, higher fidelity than the ones that can be done using these microwave signals. So the optical frequency division will allow you to really greatly exceed the coherence that you can get from the traditional microwaves. Yes.
Thank you.
Actually, while we're on that topic, before I hand the microphone to Steve, so in the kind of self-referenced version of the chip comb thing that you showed, so you pointed out how since you have kind of common mode noise in the signal in idler, but so the phase noise of the pump is largely canceled out. But you were explaining how the location of the peaks in the OPO gain spectrum are actually tied to the intensity of the pump. So do you have something where intensity noise of the pump actually then becomes a term in the frequency?
Yeah, so that's actually where, so, you know, ideally you'd like it to go to zero, but it doesn't. And that's precisely where you have residual noise that comes in, and that actually, you know, puts noise in the system. So even though I say you don't need a great pump, but at least you can do much better than you would from traditional. But ideally, you know, as always, if you want to push the limits and go, you know, to the highest fidelity, you probably still want, like, you know, sub-hertz line with lasers.
And the diode lasers are pretty quiet intensity. Yeah.
They may be, but here they'll be even better. Yeah. You're dividing the noise, and that's the key part. Is you're also you know when you actually do that frequency division, you know, it divides the frequency. But you know, if you just think about the noise that's sitting there, a little fluctuating phase term, that's also getting divided out.
When you do nonlinear optics with single photons, you have to keep track of the length of the photons. You weren't mentioning length in the various comparisons. So as one definite example, if you take a signal and idler that are entangled and you put them into a sum crystal, classically you'll get a convolution of the two spectra, but quantum mechanically you don't. You get a delta function, which is at the frequency which these photons came from. And so could you comment on what you were assuming about the length of the photons when in a few slides back?
Yeah, so here I was really assuming instantaneous nonlinearity. So the photons, depending on how you want to do the measurement, they could conceivably be pulses. You know, of course, I have a meter beam, so I over some time I have to perform the measurement of when the photon is there. Now, the photons could be, let's say, they could be produced from a microresonator cavity, where they're very narrow band. They could be below a hertz, below, megahertz, very high quality, very narrow band. And so you perform your interferometric measurement on the meter beam over a time, which is, short, let's say, compared to that coherence.
What happens depends on the photon length. And so you have to say something about it. And anyway,
I guess I have like the opposite question to Michelle. So I kind of agree with him. We don't have qubits that live 10 minutes, so I don't think we benefit from better microwave clocks yet. But like we can play these games, right? I can build paramps. I can build Duffing oscillator type frequency combs. So it sounds like you're saying I should take your like 16 gigahertz thing and then divide it down to 10 megahertz in my microwave system to replace my rubidium clock.
Exactly. So if you want to keep, which the Kerr cones I talked about, they typically kind of the lowest I could go is 10 gigahertz. They basically anywhere from 10 gigahertz to a terahertz. In which case, if you wanted to go lower, get into the more like 100 or tens of megahertz regime, there are other type of optical frequency combs, let's say from femtosecond lasers, that could allow you to divide down even further and do that. But certainly, I think even in this case here, if you can generate, any type of optical frequency division done this way, would allow you to reduce the noise by precisely the same amount. It's not, generic to optical.
Thanks. I actually had a different question, but maybe so if the way that you generate your 10 gigahertz is by multiplying up the rubidium clock. Yeah. Yeah, so if you have a very good 16 gigahertz, then you can lock your rubidium clock to that by multiplying up to 10 gigahertz and locking. And I think that's like spiritually the same, would give you the same gain. I had a question about the cell phase modulation. So I think I understand that your sort of last slide. I think I understand, maybe I understand this picture. Yes, exactly. But like, I have this other way of thinking about it where I have a Hamiltonian and I can, normal order that Hamiltonian, and everything that's nonlinear and higher order has 2 A daggers. So if I have a single photon state, it just won't see any of the nonlinearities. So what's my?
Yeah, I think so this, I would say, I don't want to say, but this is really looking at just the material, so a generic atom. And the Hamiltonian part, we never worry about it when we do it that way. We don't worry about these 2 different contributions. In fact, you just say, oh, I can renormal order it and put it all, in which case you can make it all look like this or all look like that. But I would say in the atomic system, when you do that, you can't do that because the gammas in front have a different value. So the whatever the parameter is for the A dagger squared, A squared is different from the A dagger. They have different coefficients. They have different nonlinearities. And so you can't just, we always do that all the time, but that's because we don't care where the nonlinear came from. And I can say that when you're working with almost any material, this is the only one you worry about because this is the one that's large. And again, in terms of intuition, so I didn't give any, but you can think of as a 2-photon Stark effect tends to pull the energy levels together. So that's why the chi3 is positive. And the regular AC Stark effect tends to make them pull apart. So that reduces the effective polarizability. And so that's the intuition behind why they have that particular sign. I don't know if I answered your question there, but I think when we write the Hamiltonians, we never worry about the material. And so this is, actually thinking about a real system. And that's why it's a little bit different from how we normally think about it, because it's actually taking into those account. And now the ordering matters.
Okay, great. Well, I think we've reached a nice stopping point. Let's thank Alex again. And so we're on our morning coffee break now. And so let's be sure to be back here at 1:15 for Alireza's talk.